This is section 7.2, the converse of Pythagorean theorem. I've got a bunch of words here, and if you need to write them down, you can pause the recorder to do them. I'm going to talk fairly quickly. What I want to do is I want to remind you of the Pythagorean theorem, explain to you what the converse of the Pythagorean theorem is. I'll give you a few examples based upon what I call the scales of rightness as an easy way to solve for problems involving the converse of the Pythagorean theorem. I want to give you a quick proof of the Pythagorean theorem, and then I want to let you try some examples on your own. Remember that the Pythagorean theorem states that in a right triangle, the sum of the squares of the legs is equal to the square of the length of the hypotenuse. Another way to write that is a squared plus b squared equals c squared. Remember that the converse of a statement switches the hypothesis and the conclusion, so the converse of the Pythagorean theorem states that in a triangle, if the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse, then the triangle is right. Another way to think about that is if a squared plus b squared equals c squared, then I have to have a right triangle. Okay, if the triangle isn't right, it's either got to be obtuse or acute. Well, we find that in a triangle, if the sum of the squares of the lengths of the legs is greater than the square of the length of the hypotenuse, then the triangle is obtuse. Otherwise, it's going to be acute. Once again, if you need to pause the recorder to get those down, that's fine. I'm going to move on. What I did is I copied some clip art. Normally I draw scales that don't look quite as pretty, but I'm going to draw scales, and on the left-hand side of my scale, I'm going to put a squared plus b squared. That's what's going to be inside the scale. On the right-hand side, I'm going to put c squared. And then below the scale, in this order, I'm going to put acute, right, and obtuse. And I'm going to use those to figure out what type of triangle that I have. Probably the easiest thing to do is just look at examples. So let's take a peek at example 1. Example 1 says a triangle has side lengths 2, 3, and 4. Is the triangle acute, right, or obtuse? Well, it's very important that C is our largest side. The largest side is 4, so I'm going to let C equal 4. A and B don't matter as much. A can be 2, and B is 3. Looking at my scale on the left-hand side, I need to do a squared plus b squared. Well, a squared is 4, and b squared is 9. 4 plus 9 is 13. 13 goes in the left-hand scale. On the right-hand side, I have c squared, which is 16. Now, 16 is bigger than 13. Because of that, my scale is going to tilt to the right. As it tilts to the right, I find out that this triangle must be obtuse. Because c squared is greater than a squared plus b squared, my triangle is obtuse. Let's look at the next example. Triangle has side lengths 5, 12, and 13. We're going to be acute, right, or obtuse. Well, A is going to be equal to 5, B is going to be equal to 12, C is equal to 13 because it's the largest number. C squared, 13 squared is 169. A squared is 25, B squared is 144. 25 plus 144 is also 169. The scales don't tip right or left. They stay equal, so this must be a right triangle. Hopefully you already recognize the fact that a 5, 12, 13 triangle is a right triangle. This triangle is a right triangle. Example 3. Triangle has side lengths 6, 9, and 7. Is it acute, right, or obtuse? Well, A is going to be equal to 6. B is going to be equal to, hopefully you didn't say 9, because C has to be the largest leg, or the longest leg, so B is going to have to be equal to 7, and C will be equal to 9. C squared is 9 squared, which is 81. On the left-hand side, I have 6 squared, which is 36, plus 7 squared, which is 49. 36 plus 49 is 85. The left scale is bigger than the right scale, so the scale will drop to the left. On the left-hand side is the word acute. A 6, 7, 9 triangle, or for that matter a 6, 9, 7 triangle, must be an acute triangle. Example number 4. A triangle has leg lengths of the square root of 4, the square root of 5, and 2 times the square root of 3. Is a triangle acute, right, or obtuse? The first thing I have to figure out is which one of these is the biggest leg, square root of 4, square root of 5, or 2 root 3. Well, we know square root of 5 is bigger than the square root of 4, so it gets between the square root of 5 and 2 times the square root of 3. The square root of 5 is approximately 2.236. The square root of 3 is approximately 1.732. 2 times 1.7 is 3.4. That's certainly bigger than 2. So the longest side is going to be 2 root 3. C is equal to 2 times the square root of 3. We'll let A be equal to the square root of 4 and B equal to the square root of 5. A squared, the square root of 4 squared is 4. The square root of 5 squared is 5, and so a squared plus b squared equals 9. C squared, remember to square a number means to multiply it by itself, so c squared is 2 root 3 times 2 root 3. I can write that as 2 times the square root of 3 times the square root of 3, which is 4 times square root of 3 times the square root of 3 is square root of 9, which is, of course, 3, because if I take a square root of a number and I multiply it by itself, I get the number. 4 times 3 is 12. 12 goes on the right-hand side. 12 is bigger than 9. It's going to fall to the right. A root 4, root 5, and 2 root 3 triangle must be an obtuse triangle. How do we know the converse of the Pythagorean theorem is actually true? I'm going to be given a squared plus b squared equals c squared, and I need to prove that I have a right triangle, and in this case, I'm going to prove that c is a right angle. I know a squared plus b squared equals c squared. I'm going to use that in a minute. Now, right beside this triangle ABC that I drew using my given, I've drawn another triangle, DEF. I drew it slightly differently. I started off making 2 perpendicular lines. That's why I'm able to have a right angle here. I can create two perpendicular lines, and I just let the length of one of these be A, and the length of the other one be B. The same lengths as the 2 legs on the left-hand side. The length of DE, I don't know what it is. I don't know that it's the same as C yet unless I prove it, so I just called it N. What I do know, though, is that side CB must be congruent to side FE because they both have side length A. I also know that side AC must be congruent to DF because they both have side length B. I know that in the left-hand triangle, C squared is equal to A squared plus B squared because that was given to me. The right-hand triangle, triangle DEF, is a right triangle. Because of that, I know that a squared plus b squared equals n squared, or n squared is equal to a squared plus b squared. Using the substitution property of equality, that's going to tell me that c squared is equal to n squared. Taking the square root of both sides, c is equal to plus or minus n. But because these are leg lengths, they both have to be positive, so c must be equal to the positive n. That tells me that AB must be congruent to DE, and the 2 triangles must be congruent by side, side, side. If the triangles are congruent by side, 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 all of their corresponding parts must be congruent. Angle C corresponds to angle F. Since angle F is a right angle, angle C must be a right angle also. That's what we were trying to prove, the converse of the Pythagorean theorem. All right, let's get to some examples and let you work these on your own. Example number 1. A triangle has leg lengths 4, 6, and 8. Is a triangle acute, right, or obtuse? Pause the video and give this one a try. Okay, I'm going to draw my scales. They may not be as pretty as the ones on the examples we did earlier, but here we go. I'm going to write acute, right, and obtuse. After a while, you'll get to where you don't need to put those down. You'll know what they are. Remember, this is a squared plus b squared on the left. The right-hand side is c squared. These are in order from smallest to largest, so 8 must be the C. 8 squared is 64. I've got 64 on the right-hand side. On the left-hand side, I've got 4 squared, which is 16, plus 6 squared, which is 36. 16 plus 36 is 52. 52 is definitely smaller than 64. It falls to the right. My triangle must be obtuse. Hopefully you got that one right. Let's try another example. Example 2. A triangle has leg lengths 3, 3, and 4. Are we going to be acute, right, or obtuse? Pause the video and work it on your own, please. Okay, here we go. I'm going to draw me some more scales. 4 is the biggest number. It will be over here on the right-hand side. 4 squared is 16. On the left-hand side, I get a squared, which is 9, plus b squared, which is 9. 9 plus 9 is 18. 18 is bigger than 16. I'm going to fall this way, remembering it's acute, right, and obtuse. Since it fell to the acute side, the triangle must be an acute triangle. Example 3. A triangle has leg lengths square root of 3, square root of 4, and square root of 5. Is a triangle acute, right, or obtuse? Don't fall for the fact that you know it's a 3, 4, 5 triangle is a right triangle. This isn't a 3, 4, 5 right triangle. This is a square root of 3, square root of 4, square root of 5 triangle. And we need to make sure we use the converse of the Pythagorean theorem correctly. I'm going to draw my scales. Square root of 5 is biggest. On the left-hand side, I do the square root of 5 squared. Well, the square root of 5 squared is 5. On the left-hand side, I'm going to put the square root of 3 squared plus the square root of 4 squared. Well, the square root of 3 squared is 3. The square root of 4 squared is 4. 3 plus 4 is equal to 7. 7 is bigger than 5. This triangle must be acute. Problem number 4. Triangle has leg lengths 3, 3, and 3 root 2. Is it going to be acute, right, or obtuse? Pause the video and give it a shot. Okay, I put down my scales. 3 root 2 is bigger than 3 because the square root of 2 is greater than 1. And so on the left-hand side, on the right-hand side, I'm going to have 3 times the square root of 2 squared. Remember, that's 3 times the square root of 2 times 3 times the square root of 2, which is 3 times 3 times the square root of 2 times the square root of 2, which is 9 times 2, which is 18. The easy way for me to do that, I always take the number that's not underneath the radical, multiply it by itself, 3 times 3, and then multiply that product by what the number underneath the radical. Works every time. 3 times 3 times 2 is 18. On the right-hand side, I'm going to have a squared. Doesn't matter which one a and b are, they're the same number. A squared is going to be 3 squared, which is 9. B squared is 3 squared, which is 9. 9 plus 9 is 18. It doesn't fall to the acute side. It doesn't fall to the obtuse side. This is a right triangle. A 3, 3, 3 root 2 triangle is a right triangle. We'll learn more about that when we talk about 45, 45, 90-degree triangles later in the quarter. Okay, I hope this made the converse of the Pythagorean theorem easy for you, and get to work.